Well, I want to welcome you and thank you for taking the guts to run away from that hurricane and come over here from the shore to get to the talk tonight. My name's Terry Oswald. I'm the head of the Physics and Space Science Department, and I'm here to introduce the man that needs no introduction. You know, when they say they don't need an introduction, you're about to introduce them. Dr. Matt Wood has been a professor here for Lord knows how many years.
20.
I was going to say 20. And he just had a big birthday, so give him a round of applause. Dr. Wood is a specialist in the computational and modeling and theory of stellar systems, close binary stars in particular, where matter is flowing from one to another. And he may or may not mention some of that aspect here in tonight's talk, but he is going to talk about something that made it all possible for us to be here tonight. If stars hadn't been turning hydrogen into helium and heavier elements after that, we wouldn't be here because we're made out of those heavier elements. Those are key to the origin of life. And as Carl Sagan used to say, hydrogen is a colorless, odorless, tasteless gas that, given long enough, turns into people. How that happens is up to Dr. Wood to tell us tonight.
All right. Thank you, Terry. All right. Thank you, everybody, for coming out. Let me shut off the music. All right. So, once again, welcome to my favorite, best-looking, smartest people in Melbourne, Florida, and surrounding communities. Thank you so much for coming. Terry mentioned I had a birthday. I have traveled, I did the calculation, 400 billion miles in my life. 50 years, traveling at 370 kilometers per second. As we orbit around the sun orbits around the galaxy moves through space. So it's actually pretty impressive, right? Almost 80 billion years per year. So there you go. Miles, 80 billion miles per year. So, today I want to talk a little bit about cosmic nucleosynthesis. Let me cut the lights here. Hopefully this works and leaves us with a little bit of ambient light. So I want to talk about cosmic nucleosynthesis, right? That's what Carl Sagan meant when he said, we are all star stuff, right? And as Terry said, you give hydrogen long enough, let it work with gravity, and we can eventually get heavy elements and get people. So we want to talk about how that actually happened, and it happens in stars. The Big Bang itself only created some hydrogen and helium, tiny little bit of lithium. Every heavy element, carbon, etc., nitrogen, oxygen, every heavy element in the universe has been synthesized in the core of a star. So that's what we mean by we are all star stuff. So I want to talk about stellar evolution, nucleosynthesis, how stars evolve, star formation and death, galactic chemical evolution, where are there more metals? Astronomers, we like to keep things simple. We're simple people, but we're nice. So hydrogen, helium, metals, right? So when I say metals, that's just everything except hydrogen and helium. And then what does this say for extraterrestrial life in the galaxy? And have they been here to visit us? Can we go there to visit them? Right. So we'll look a little bit at what it takes. Interstellar Travel 101 is the name of that slide. Okay, so in the beginning, there was the Big Bang, right? T equals 0, there was the Big Bang. And at about 10 to the minus 43 seconds, so just a little primer on scientific notation, because I'll be using a bit of it. So that is 0.43 zeros, and then a 1. Okay, so tiny, tiny fraction of a second. That's when physics as we currently understand it begins. So first of all, very impressive, I think, that we know physics pretty well back to that energy level. At 10 to the minus 32 seconds is when we had the inflationary epoch, and that's when the strong nuclear force decoupled from the other three forces. I think Dr. Oluche in his talk later this semester may talk about that a little bit. He also we've touched on it in previous lectures. At 10 to the minus 10 seconds, and so that's 10 zeros and a 1, the electromagnetic and weak forces decouple. There's 4 forces in nature: the strong nuclear force, the weak nuclear force, electromagnetism, and gravity. Right? I'm not really talking about that today, so. And then at about 0.001 seconds, 10 to the minus 3 seconds, matter annihilates antimatter, right? Because the Big Bang produced pretty much equal numbers of protons and antiprotons, electrons and anti-electrons, which are called positrons. But at 10 to the minus 3 seconds, they all annihilated except for 1 part per billion matter over antimatter. So for every billion antiprotons, there was a billion plus 1 protons. And that's what's left. And then at about 3 minutes, actually a few minutes, fusion is pretty much done. It's actually like 15 minutes. I'll show you the slide in just a second. Fusion is pretty much done, and we're left with roughly 3/4 hydrogen by mass, 1/4 helium by mass. There's a little bit of lithium, but it's 1 part per billion. Right? So for every lithium nucleus, you've got a billion hydrogen nuclei. Okay, so tiny little bit of lithium. And that's it. Okay, so this is kind of a complicated diagram here, but what this is sort of showing is we're going from t equals 0, and then we're moving up in time. And so this is just summarizing what I just said. So here's 10 to the minus 43 seconds. And before that time, all those 4 forces were 1 force. And boy, we just really don't understand that at this time. 10 to the minus 38 seconds, 10 to the minus 10 seconds. All right, some of these boundaries are a little bit fuzzy. And these are kind of what, was going on. And so at 3 minutes, that's when we've got our, era of nucleosynthesis. And that's where it's hot enough, it's dense enough in the early universe that protons can collide with protons and make deuterium, and deuterium can collide with another proton and make helium, and all this stuff we're going to talk about. But the universe is expanding pretty rapidly, and after about 10 minutes or so, the universe is now too cool and not dense enough, and there's no more nuclear reactions going on. We have to wait for stars to form to have any additional reactions. Okay, so then the era of atoms. After 500 million years or so, we can start to form galaxies, start to form stars. That's when the very first stars in the universe occurred, and we've had stars ever since then. Like that? So Big Bang nucleosynthesis. So it was Gamow, Alpher, and Herman originally proposed that all the elements that we see were created in the Big Bang. Now it turns out you can't do it, and the reason is because to get to carbon, you have to go through an unstable element, which is beryllium. So the nucleus of beryllium, almost as soon as you make it, it'll fall apart again into 2 helium nuclei. In a star, it can be dense enough that you'll always have a few of those beryllium atoms, and every once in a while the beryllium atom exists, before it falls apart, gets hit with another helium atom, makes a carbon. That's stable. But there's not enough time, not enough density in the Big Bang to have that happen until you get nothing heavier than beryllium. You make some beryllium, but then it falls apart again. So Burbage, Fowler, and Hoyle, which is sometimes abbreviated B²FH, they worked out stellar nucleosynthesis, where, in stars you've got more density, right? Things are more tightly packed. Longer time scales allows this triple alpha process. An alpha particle is a helium nucleus, 2 protons, 2 neutrons. That's an alpha particle. Combine 3 of those, you get carbon, right? Carbon 12. So we're going to talk about atomic weights, right? The weight of carbon is 12. The atomic number for carbon is 6. It has 6 protons in the nucleus and 6 neutrons. And then there's 6 electrons in the cloud around it. So just a couple of notes here. So when I say, helium, 3 heliums make a carbon, I'm not really talking about the entire helium atom. We're always talking about just the nuclei. Okay, so the electrons are kind of irrelevant for what we're talking about here. Right? And I'm also going to use the term nuclear burning. Right? Now, burning, as we all know it, right? Strike a match, right? Light the stove, right? Gas stove. That kind of burning is an oxidation process. That's a chemical process. So astrophysics just adopted that term, right? We're talking about nucleosynthesis, nuclear fusion, but we just simply refer to it as burning, right? We have this fuel, hydrogen, that we're turning into helium, for example, in the core of the sun. So we're burning hydrogen to helium, but it's not, right? Totally different process, but same word. Okay, so Burbage, Fowler, and Hoyle, their model could not produce enough helium to explain the helium in the universe. So now we understand that both these groups had a piece of the puzzle, right? The helium was created in the Big Bang, and everything else is created in stars. Okay, so I got a few nice little simple equations here. Don't run away screaming. I've locked the doors. No, I haven't locked the doors. So we start off before 1 second in the history of the universe, and we've got a proton plus an electron, that's the E with the little minus sign, and that will give us a neutron plus a neutrino, and you see that arrow goes both directions, so that also means that you can have a neutron, add the neutrino, and you can get a proton and an electron, right? So those reactions go forward and they go backwards, right? They're going backwards and forwards all the time. And then at about 1 second, it's cool enough that the reaction can only go one way, and so we get a neutron decays into a proton plus an electron plus an antineutrino, and that has a half-life of about 615 seconds. So if you were to just pluck a neutron out of an atom and just set it down on a table, in about 10 minutes, on average, it would decay into a proton. Right? So neutrons have to be in nuclei in order to be stable. So a little bit later, at a proton plus a neutron, that can give you a deuterium nucleus, and that's just a hydrogen nucleus with 1 proton and 1 neutron. Okay, so a heavier form of hydrogen still has 1 electron, so it's still hydrogen. And that gamma symbol, that's a photon, right? So it gives off a high energy photon. Once we have deuterium, we can get these further processes where we get a deuterium plus a neutron gives us hydrogen 3, and then the hydrogen 3 plus a proton gives us helium 4. So now we've got our first helium in the universe. Now that first reaction, the proton plus the neutron making the deuterium, that's really slow, right? It's because it's got that, that first one with the neutrino means it's pretty unlikely. Coming on down to that box again, the deuterium plus a proton can give us a helium 3, and then the helium 3 plus a neutron can give us helium 4. Okay, so after about 15 minutes, right? So this is 15 minutes into the history of the universe, which is now 13.7 billion years. Okay, so after 15 minutes, we're done with primordial nucleosynthesis. It's too cold. Now we did create some hydrogen-3 and some beryllium-7, but those have half-lives of about 12 years and 53 days. And so after a year, they're just gone, right? They've all decayed. Okay, so I want to show a bigger version of this plot here. And so this is showing the logarithm of the time. So this is 1 second, right? 10 to the 0 is 1. 10 to the 1 is 10, 100 seconds, 1,000 seconds, 10,000 seconds. Okay? And this is showing how all the different elements evolved. So on the left-hand side is basically what was created in the Big Bang. And you can see protons, right? That's the hydrogen, the line on the top. And then there's neutrons. And at 1 second, we already have a little bit of deuterium. And then at about a time of 100 seconds, so minute and a half, our deuterium peaks. And then as we come over here at 10,000 seconds, we've got mostly hydrogen, some helium, that deuterium, which is going to decay away, tiny little bit of lithium. Well, this is what we have now. If we have any chemists in the office, you're welcome. Any chemists in the audience? Okay, so this is what we have now. All right, crowning achievement. So we've got all these different elements, all these different properties. We have different isotopes of different elements, right? So you've heard of carbon-13 dating, right? Well, I originally mentioned carbon-12. So what's the difference between carbon-12 and carbon-13? It's one neutron, right? It's just one neutron extra. So we've got 7 neutrons and 6 protons. So it's the same element, same number of protons, same number of electrons, different element. Behaves a little bit differently. All right, so we've got all these elements. Where'd they come from? Well, Terry gave away the punchline. They all came from stars, right? All the elements heavier than lithium were created in the cores of stars and then redistributed back into the interstellar medium to get incorporated into the next generation of stars. So without stars, no planets, no humans. Okay, so how does it work? The very first generation of stars would have had no metallicity, just hydrogen and helium. We have never observed a star with 0 metallicity. We've observed it with small metallicity, like 1 part in 100,000, but not 0. So low-mass stars live a really, really long time. A star that has a mass of 1/10 the mass of the sun, it will live 1,000 times longer than the current age of the universe. Right? So they live a really, really long time. The sun is halfway through its life. It's 4.6 billion years old. Right? But these low-mass stars, boy, they're just going to live forever. And there's a lot of them. Every time you go a factor of 10 in mass, it's a factor of 200 in numbers of stars, and it's weighted towards the low-mass stars. So lots and lots of low-mass stars. So what this means is that if we had created low-mass stars in that first generation, we would see them. They'd still be around. Right? So they're not here. So that first generation of stars, we think, formed very massive stars, maybe hundreds of solar masses, that lived a very short time, went supernova, distributed heavy elements into the interstellar medium, which then went into the next generation of stars. So the model suggests that the first generation, very massive, lifetime short, and so these extremely metal-poor dwarf stars that we do see may be the second or third generation of stars. Right? So maybe in order to form stars of a low mass, you actually have to have the metals. Right? And one of the things that we can do is we can look at these extremely metal-poor stars, and we can look at the isotopic abundances, and that actually kind of gives us a clue, you know, did those elements come from a supernova, or did it come from a more quiet stellar evolution called the slow process we'll talk about. Okay, so stellar astronomy talks. Gotta have an HR diagram or 2 or 3. So here is an HR diagram. This shows 20,000 points, 23,000 points. And so this is showing everything from, here's our main sequence. This is where most of the stars reside. Right, most of the stars are there. We have some stars up here in the giant region. Lines of constant radius run roughly parallel to that main sequence. So as we go up into that corner, we've got big, bright stars. As we come down into this corner, we've got little, dense stars. So stars actually evolve. This is just showing on the vertical axis, it shows the luminosity, so that's the brightness. And then on the horizontal axis, we're plotting on the bottom axis here, it's color. Top axis, we've got spectral type or temperature. But basically, temperature increases to the left. So these stars are, right in this corner, it's hot and it's dim. Up in that corner, it's cool, but very, very bright. And then up in this corner, it's hot and bright. Right? So up at the top end where the white stars are, those are the very massive main sequence stars. And then down here are these red dwarf stars that live forever. Right? They're just very miserly with their energy. And then at, if you see the 1 there and kind of go across to the line, that's where the sun is. Right? So the sun's a fairly typical star. Also in this diagram, the density of points indicates where stars spend the most time. So 90% of all stars are on the main sequence. Right? Stars spend 90% of their lifetime on the main sequence, burning hydrogen and helium. Okay, so here's another HR diagram. This one's a little bit more schematic. And this is showing how a star like the sun might move through the HR diagram. Now the sun isn't actually moving, it's just that the surface temperature and the brightness are changing as the star evolves. As we convert hydrogen to helium, that changes the structure of the star. So on the main sequence, we're burning hydrogen to helium, and then we evolve up to the subgiant branch, and at that point, right along in here, we've got a helium core, right, because hydrogen burns to helium, so it makes this helium core, and around that we'll have hydrogen burning in a shell, and then outside that we'll have just the rest of the star. It'll be a giant star at that point. And in fact, when the sun is up at the tip of that red giant branch, the outer radius of the sun will be somewhere between the orbits of Venus and the Earth. The temperature at the Earth will be much higher than the boiling point of water. Right? So the oceans will have boiled away by that time, and we will have had to move to Mars or something. Get a little bit further away. So then at this tip of the red giant branch, that's when we start burning helium. We settle down here, we're burning helium quietly in the core, hydrogen burning in a shell around it, and then we come up here, and at this tip of what's called the asymptotic giant branch, now we have an inert carbon-oxygen core, and then a helium-burning shell, and a hydrogen-burning shell, and then the rest of the star. And at this point, the outer layers of the sun will probably be at about the orbit of the Earth. And then, for a solar mass type star, some oscillations set in, wind mass loss, and everything except that carbon-oxygen core drifts away into space. So before that happened, we've had deep, deep convection, right? That entire outer layer is convective. And so nuclear process material is getting up into that envelope, and then it's being dispersed back into the interstellar medium. So by that process, we've managed to put some heavier elements back out into the interstellar medium. But so here's what powers the stars. It's this nuclear fusion. And so here's the net reaction. We take 4 hydrogens, which is to say 4 protons, because remember we're just talking about the nuclei. Take those 4 protons, that gets converted to a helium-4 nucleus, and then we also get 2 positrons, which are anti-electrons, 2 neutrinos, and 2 photons. Right? So that's our net reaction. And the way that this works, okay, so we all know the equation E equals mc squared, right? We've seen that's one of those iconic things. What that means is that energy has a mass equivalent, and so what we're doing here is the right-hand side weighs a little bit less mass than the left-hand side. And that difference in mass times the speed of light squared is the energy produced in one fusion reaction. Okay? So that delta mc squared, so the mass is 0.7% of the mass of the 4 heliums, right? So for every 4 heliums, multiply that times 0.007, multiply that times c squared, that's your energy per reaction. Okay? So to power the sun, we've got about 10 to the 38, 1 followed by 38 zeros, reactions occurring per second to support the solar luminosity, right? Lots and lots of reactions. So that is about 10 to the 11 kilograms, right? 0.1 trillion, 100 billion kilograms. I mean, it's a small number when you compare it to the national debt, but so that amount of kilograms per second of helium is created. That's equivalent to about 5,000 cruise ships, or if we convert 30 cruise ships a second completely into energy, right, mc squared, then that's the luminosity of the sun. I used to say aircraft carriers, but then I thought, people know cruise ships, right? So we'll just go with those. More people in this room have been on a cruise ship than on an aircraft carrier, I'd be willing to bet. Okay, so here's a nice little pictorial depiction of what actually goes on. So we start up here, 2 hydrogens combine, they make a deuterium atom, and it kicks off a neutrino, kicks off a positron, which is, again, that anti-electron. And then we take that deuterium, combine it with another proton, and that gives us our helium-3 nucleus and kicks off a photon. Notice that this reaction here says 1.4 times 10 to the 10 years. That just means it's a very low probability. But there's an awful lot of hydrogen in a star, so it happens, right? And it's that neutrino that makes it kind of a low probability. So there's our helium-3. Combine 2 helium-3s, that gives us helium-4, and then we kick out 2 protons. Okay? And again, that's what powers the sun. That's what powers all the stars on the main sequence. There's another process, that's the proton-proton reaction. There's another process called the CNO cycle. And you can start anywhere in the cycle, but if we start here with carbon, add a hydrogen, we get nitrogen, and then we're back to a different isotope of carbon, and then nitrogen, and oxygen, and nitrogen again. And at the end, we kick off a helium-4, and it's the same reaction. We've added 1, 2, 3, 4 hydrogens. And the carbon, nitrogen, oxygen are acting as a catalyst, right? We're not creating or destroying CNO in this process. They're just kind of acting as intermediaries. So the proton-proton one, the one I showed on the previous slide, that dominates in low mass stars, 1.5 solar masses and less. So our sun has that much simpler thing going on. And then stars with masses more than 1.5, they're the ones that have this CNO cycle. Okay, and there's the equations. Okay, sure. I want to read this. So the total energy available, we take, right, so there's our E equals mc squared. Again, we've got a couple factors of alpha and beta. Alpha is that efficiency, 0.7%. Beta is the fraction of the star that we burn before it has major structural changes. And so when you do this calculation, you get 10 to the 44 joules. And so, we tend to use British units for a lot of things. But we know joules, right? A 100-watt light bulb, 100 watts is 100 joules per second. Right? So just a measure of energy. So we can calculate the solar lifetime, take this energy, divide it by the luminosity of the sun, and we get about 10 billion years. And we're about halfway through that with the sun. And now if we put in what the luminosity is as a function of mass for all stars on the main sequence, it goes as mass to roughly the 3.5 power. So then the lifetime goes as 10 to the 10, mass to the minus 3.5 power. Okay? So that's like, cubed, basically. And so massive stars live 1 million years or less, right? So a 20 solar mass star, do that equation, you get something, less than 1 million years, right? So that's quick, very quick. These low mass stars put in 0.1 solar masses, and like I said earlier, 1,000 times the age of the universe, right? Long, long time. So when the universe is 1,000 times older than it is now, there will be a lot of these little dim red stars, and that's it. Okay, so then we've got helium burning. We combine two heliums, we make a beryllium. Now that's unstable, but if you hit it with another helium, well, it's existing as beryllium, you can make carbon. And then once you have carbon, you can add another alpha particle, this helium, and get oxygen. Add another alpha particle, you get neon. Add another alpha particle, magnesium, etc., up to silicon, up to iron. Now iron is the most tightly bound nucleus that we have. And so when I show you what elements there are in the universe, you're going to find that, the carbon, oxygen, neon, magnesium, we got a lot of that, right? A lot of that in the universe, and it's from that process. But in addition, we also have a lot of free neutrons around inside stars, and neutrons have no charge, so they can just be captured by a nucleus, right? Just got a carbon-12 nucleus, neutron comes along, okay, I'm staying around. Right? And so now you've got carbon-13. Add another nucleus, carbon-14. Well, carbon-13, carbon-14, those are radioactive, meaning that they can decay. And there's two ways that they can decay. They can give off an alpha particle, we'll call it alpha decay, kick off an alpha particle and a gamma ray, or they can beta decay and kick off an electron. And so if you have carbon-13 beta decays, what happened is that this new nucleus has one more proton and one less neutron. So one of those neutrons got converted to a proton, and so now it's, let's see, what's above carbon? Anybody know what's right after carbon? Nitrogen? Okay, so then you get the nitrogen, okay? See, I should know this stuff, but hydrogen, helium, metals, that's where I'm coming from. Okay. All right. So when we have these decays, those also, they're radioactive, meaning that the nucleus that we're left with is more stable. All right. And this is how we can build up different isotopes. And so there's this thing called the valley of stability, and this is a nice little plot that I found. And so you just keep adding these neutrons, and you'll get alpha decays, beta decays. You can also add protons and alpha decays, beta decays. And so in this valley of stability, so we're increasing, going to heavier and heavier elements as we go back in here, and we can add more neutrons over here, we can add more protons over here. But if you go too far up, then you get a radioactive decay and it brings it back down. All right, so that's one way to look at it. Another way to look at it is, let me show this plot first. Right, so we're looking at neutrons increasing on the horizontal axis, protons increasing this way, and so these black spots are where all the stable elements are. And then in our laboratories, we have explored all of this tan region, right? Because now we can just, put a sample of whatever element and just fire neutrons, just fire a bunch of neutrons at it and see what happens, right? Study it. All right, so that's that valley of stability. So we've got two ways of adding neutrons. We can add them slowly or we can add them rapidly. And what determines slow and rapid is if we're adding neutrons so that there's plenty of time for a beta decay, right? So it's the core of a star or one of these hydrogen or helium burning shells, right? So it's slow, right? There's plenty of time. Rapid is a supernova explosion. So if it's slow, then you capture a neutron, and then before you capture another neutron, you got plenty of time to beta decay. Right? If it's rapid, then you're just getting flooded with neutrons. And so you don't have time to beta decay before that next neutron comes in. And so those two different processes give you different isotopes when things finally settle down. And we can tell the difference, right? And that's one of the things we're trying to do is we study the elemental abundances in stars in very great detail, and we try to figure out what is the history of star formation in the galaxy. How many of those elements came from supernovas? How many of those came from, solar type stars that just ejected a nice gentle wind. Okay, that's one of the things we try to figure out. Okay, so there's a value of stability. Here's our nuclear binding energies, and this really tells the story. So we combine hydrogen into helium, and that's a big jump here, right? So that's that big delta MC squared. That's that energy release. And then we take our 4 heliums and we jump up to carbon, and that's about 1/10 of the delta M. And so the helium burning phase lasts about 1/10 as long as the hydrogen burning phase. And then we burn, add another nucleus, and we get the neon, and then the chlorine, and up to iron. And you notice iron is the peak. Iron is the most tightly bound nucleus that we have. So if you do anything with iron, it takes energy, right? As you're building up to iron, you get energy out. If you start with uranium, right, come over here to uranium. If uranium splits in 2, then we move up this curve, we get energy out, right? That's how our nuclear reactors work, is radioactive decay of uranium. So it's just spontaneously fissioning, and then we capture that energy and we use it to drive steam turbines. Right? That's how a nuclear reactor works. But you can't do anything with iron. You have to put energy in. So right before a supernova, this is a schematic of what a star looks like. Once you get about 1.5 solar masses of iron at the core of a star, it's done for. And in fact, once you start burning silicon, you've got about 2 days before the supernova explosion. Right? So I always like it in the Star Trek episode where they're like, yes, we're studying this star. It's about to go supernova. And the thing is, you like that? That's my science guy voice. So once it starts burning silicon, right, if you could say these neutrinos come from silicon burning, you actually could say, yes, in 2 days that star is going to go supernova. Okay. Once you got iron core, now you can't do anything with iron and get energy out. It soaks up the energy, right? And all this time we've been releasing energy, and that's kept the core hot, and that's kept the star supported. Once you get that 1.4 solar masses of iron, any further reactions absorb energy, and so now you steal your pressure support, that core collapses, and it collapses in a small fraction of a second. And it collapses down to a neutron star. All right, so the electrons get squeezed onto the protons. You form this neutron star. Now, the oxygen layer, it is like the coyote in a Roadrunner cartoon. It has no idea what just happened. Right? If it looked under its feet, it'd say, there's nothing holding me up anymore. Right? And so the star begins collapsing inward, and we get a runaway explosion as it effectively bounces off that neutron star, and that gives us the detonation wave that gives us the supernova explosion, the flood of neutrons, and all those isotopes that come from the rapid nuclear reactions. And those get dispersed into space. And because it's so rapid, that's where we get all the elements heavier than iron. Right? Those are coming from the supernova explosion. So the very first proof that stars created elements, there was some technetium that was discovered in some star back in about 1950, and it was a radioactive technetium, right? They could tell from the spectral line that's what this thing is, and it has a relatively short half-life, so it had to have been created in that star, right? And then brought up to the surface by convection. Okay, so we've got our supernova explosions, we've got our red giant winds that can disperse the stuff back into the interstellar medium. These are some evolutionary tracks just showing, I showed you one before, and so here's like a solar type star, comes up there, helium ignition. The massive stars tend to loop back and forth like you see over here. And basically every time it turns around, it started to burn a new element. All right, so we get that onion skin structure. Okay, so it's been a long time since I've shown you some pretty pictures tonight, so I'm sorry about that. So this is Eta Carina. If you came to the talks last year, I think we actually had 2 talks where people were talking about this one. This is probably the most massive star that we know of right now. 80, 100 solar masses, maybe, something like that. And this is a wind. Basically, the whole star just went, right? And kind of kicked out this dust shell about 100 years ago, something like that. Right? And there's a lot of solar masses just in that dust shell. And then if we image a little bit deeper, we can actually see that it's not the first time this has happened, right? So this thing is actively pushing stuff back out into the interstellar medium. Those stars that are in the upper left-hand corner of the HR diagram, they're very hot and they're very big. And so there's so much luminosity that radiation pressure, just like we might use for a solar sail, radiation pressure actually expands the atmosphere and drives a pretty strong wind. So we get mass loss while the thing is evolving. So this is another star that's expelling matter. Another star, these are called Wolf-Rayet A stars, very massive, have a lot of mass loss going on. This is a supernova remnant. Right, so this is not what it would look like if you were actually there, right, and kind of enhance things to make it pretty. But this is a supernova remnant, so the star actually blew out into the interstellar medium. We get this filamentary structure, and so some of this is powered by radioactive decay. I believe the glow that's interior is actually from the Chandra X-ray satellite. So those are, gamma ray photons caused by the radioactive decay causing that glow, right, and all that filamentary structure. And so that can then be swept up and form into the next generation of stars. So the metal content in the galaxy just increases with time. Okay, so some more pretty pictures, another supernova remnant. There's actually in the news just yesterday, new supernova that went off. It's actually relatively close. Might even be as bright as 6th magnitude at its brightest. So you could probably see it just with a nice pair of binoculars. Is it in the northern hemisphere?
M100, if I remember right.
M100, okay. These guys in the Melbourne Astronomical Society can help us all out and tell us where to point our binoculars. I can mail something out if I find something, okay. But that would be pretty neat. Because was it 30 years ago, 1987, there was a supernova that was just in the Magellanic Clouds, but that was not visible from the northern hemisphere. Okay, so here is the summary of our story. We start with an interstellar cloud. That makes protostars, and small stars like the sun evolve. They have they're red giants. They have wind mass loss. They do a planetary nebula. They end up as white dwarf stars. If they're in a binary system and they're accreting mass, then it might push it over the maximum mass of a white dwarf star. We get a type 1a supernova, which is what this recent one was. Right, so that's an exploding white dwarf star. Again, the white dwarf is basically carbon and oxygen, collapses down to do a supernova explosion, and we again get a detonation wave and all kinds of radioactive elements coming out of that. If we've got a large, massive star, we'll get a red supergiant. Supernova explosion should leave behind a neutron star or a black hole. This one also kind of shows what's going on. So the massive stars make the blue supergiants, supernova explosion, black hole. All of these things are feeding back into the interstellar medium, right? So it's the cycle of life. That's what it is. Kuna Matata. The very lowest mass objects are the brown dwarfs, and they have less than 1/10 of a solar mass, and so they never have nuclear burning. They just keep collapsing on down. Right? So they do not return any mass back to the interstellar medium. So we're not that interested in them tonight. Yeah, it's funny. The people that actually work on brown dwarfs, I have found, generally hate the term brown dwarf. It's like, please call them something else. So this is showing the abundances in the solar system. Again, this is a logarithmic scale. So every tick mark here is a power of 10. So there's hydrogen, most abundant. and then helium, next most abundant. Notice there's hardly any lithium, hardly any beryllium, because, right, unstable, the beryllium. There's boron. And then we got lots of carbon, lots of oxygen, neon, silicon, sulfur, argon, calcium, right, salt, well, it's sodium, titanium, up to iron, right, lots of iron, right, because basically stuff stops at iron. When you have supernova explosions, those throw out a lot of iron. And then the stuff past iron, you know, just not very much of it. But it's there, and it was created by supernova explosions. Okay, so the metallicity builds up with time, right? We started with just hydrogen and helium from the Big Bang, and then stars have synthesized all these heavier elements. The metallicity is also higher as you are in a higher stellar density, which means that the metallicity is higher as you go closer to the center of the galaxy. And again, you got to have metals to have planets. And as far as we know, you got to have planets to have life. You certainly have to have metals to have life as we know it. So this is one of those wonderful National Geographic inserts, and shows our galaxy right over here, right? You are there. And actually on the web, this is, you know, like 3,000 by 2,000 pixels. It's a huge, huge image. But this is actually a reasonably accurate model of what our galaxy would look like from the outside. We do have a bar at the center of the galaxy. Okay, not the kind you're thinking of. College students. So it's a dynamical bar at the center of the galaxy. And we can kind of see it end on, and we're close to a spiral arm, but we've actually gone around the galaxy about 20 times in the lifetime of the solar system. Okay, we're orbiting around. And so the fact that we're near a spiral arm is just coincidence. Right? So those bright patches there are where we have very active star formation, and those are the very massive short-lived stars, right? So the typical supernova explosion occurs right in those spiral arms because those stars are very short-lived and they don't go far from home before they destroy themselves, right? So they're the reckless kids in high school. Right? All of us are the responsible. I can't go any farther with that. All right, so there's our Milky Way galaxy. So star formation started first down near the center of the galaxy because the densities were higher there, so should have built up metals first there, so should have had planets there first, and probably life. All right. So I just wanted to spend a couple minutes talking about this. You know, I got the whole idea to do this talk from this Carl Sagan video that came out last year, and I'm going to show it to you because I like it. But, you know, and the We Are Star stuff, that was 1980, so I was freshman in college, right? And I wasn't thrilled with it because, go figure, I was, you know, arrogant young man, physics major, and it's like, pah, television celebrity. But he actually knew, he really knew his stuff. I mean, Carl Sagan was co-author on 350 published refereed papers and, you know, lots of books and stuff. So he really did know his stuff. And cosmos really was a great thing at the time. So we need carbon and oxygen. So the very first generations of stars could not have had enough metals to form rocky planets, oceans, things like that we think. So let's look at some time scales. Our solar system is about 4.5 billion years old. The galaxy itself, 13.5 billion years old. The universe, 13.7. So the galaxy is at least 12, right? And so we probably have had stars in the galaxy capable of, you know, forming late enough to actually have enough metals to form planets for probably 10 billion years, right? The history of the galaxy. So, you know, we could have some planetary systems that were 10 billion years old, right? Twice as old as ours. Okay. Now, we also know, another recent discovery that was in the news in the last week or so, that it really looks like we had life on this planet just as soon as it was possible for it to not be destroyed. right? There was this era of heavy bombardment where, things just kept crashing into the earth, and so that's not real conducive to life. But about 100 million years, 200 million years after that was done, life, right? We've got it in the fossil record, right? So if that is typical, and I suspect it probably is, it's actually kind of driven by the second law of thermodynamics, but I don't have time to go into that, then life may be very common in the universe. Carl Sagan was a very early proponent of this search for extraterrestrial life, and if you think about it, if we had real proof, right, if we knew that there was another life form out there, I think it would change a lot of people's perceptions about the everyday things that, we think are problems, but maybe really aren't, right? Nothing like a different them to make us all pull together, right? I mean, it's maybe not totally pretty, but, it would work the right way. And I think we're safe both ways. So there's this thing called the Drake equation, and you may have heard of it, you may not have heard of it. I'm running out of time, so I'm not going to go through it, but it's a very crude way to estimate the number of intelligent planets capable of communication that there might be in the galaxy. And depending on what numbers, if you type Drake equation calculator into your favorite search engine, you can type in your own numbers and see what you get. Okay, so are they here? These UFOs, I keep hearing about them. Is it real? Can we go visit them? Well, let's look at what it takes. So we got big distances. The closest star is a little over 4 light years away. So if we travel at 1/10 the speed of light, it's going to take us 50 years to get there. All right? So you leave at 20, you get there, you're 70. So you're ready to retire. Right? Okay. Hopefully they've got nice beaches when you get there. So now the Voyager spacecraft is our fastest moving spacecraft. It's traveling at 1/80,000th the speed of light. And so it would take 72,000 years to get to Alpha Centauri. It's not pointed in that direction, but that's how long it would take, right? So we're not going to we're not going to use conventional propulsion. We're not leaving anytime soon, right? So just to accelerate, probably a 100-ton ship, right, which would actually be kind of small, right? It's a 50-year journey, so you need to take a few people, right? So 100 tons, right? Because a car is 1 ton, right? So this is not a super heavy thing we're talking about. We need over 10 trillion kilowatt hours of energy. So that's the world's total energy output for a full year to accelerate up to that speed. And then, yes, you need that much energy to slow down again at the other side. And you have to carry it with you. Now, it's only 12 cents a kilowatt hour from Florida Power and Light. However, the extension cord is a problem. And another problem is if you run into, say, just a small pebble at 1/10 the speed of light, that's gonna hurt. Right? So there are some problems. So for now, personally recommend, let's work on the search for extraterrestrial life, right? Radio could be the way that they would communicate. And, we can pretty safely broadcast because, we really do understand physics reasonably well. There's not going to be any breakthroughs like, wormholes and stuff like that, right? So don't think that's coming right around the corner. Now, there is, I mentioned there's this little Carl Sagan video that I saw, and I really liked it, and that actually what got me thinking about doing this whole talk. And so this website, Symphony of Science, they are the only people using auto-tune in a way that I find acceptable.
I'm not very good at singing songs, but here's a try. If you wish to make an apple pie from scratch, you must first invent the universe. Space is filled with a network of wormholes. You might emerge somewhere else in space.
The sky calls to us. If we do not destroy ourselves, we will one day venture to the stars. A still more glorious dawn awaits, not a sunrise, but a galaxy rise. A morning filled with 400 billion suns. The rising of the Milky Way. The cosmos is full beyond measure. Elegant truths of exquisite interrelationships of the awesome machinery of nature. I believe our future depends powerfully on how well we understand this cosmos, in which we float like a mote of dust in the morning sky.
But the brain does much more than just recollect. It intercompares, it synthesizes, analyzes, it generates abstractions.
The simplest thought, like the concept of the number one, has an elaborate logical underpinning. The brain has its own language for testing the structure and consistency of the world. A still more glorious dawn awaits, not a sunrise, but a galaxy rise. A morning filled with 400 billion suns. The rising of the Milky Way. The sky calls to us. If we do not destroy ourselves, we will one day venture to the stars.
For thousands of years, people have wondered about the universe. Did it stretch out forever, or was there a limit? From the Big Bang to black holes, from dark matter to a possible big crunch, our image of the universe today is full of strange sounding ideas.
How lucky we are to live in this time, the first moment in human history when we are, in fact, visiting other worlds. A still more glorious dawn awaits, not a sunrise, but a galaxy rise. A morning filled with 400 billion suns. The rising of the Milky Way. A still more glorious dawn awaits, not a sunrise, but a galaxy rise. A morning filled with 400 billion suns. The rising of the Milky Way. The surface of the Earth is the shore of the cosmic ocean. Recently, we've waded a little way up, and the water seems inviting.
That is pretty damn cool.
All right, well, thank you very much.